So, lag lead control. So they're similar, or I guess analogous, you could say, analogous to PID controllers, but can be instantiated with passive electronic circuits because they do not contain pure differentiators or pure integrators, which can be an advantage sometimes. Sometimes you don't maybe have a lot of extra power, or it's hard to access the extra power, and you'd like to just come up with a completely passive circuit that controls something, which is pretty cool. So, the design process is very similar to that of a PID controller. And so we go through those steps. First off, evaluate the transient performance with a P controller. So we do what we can with the P control, and that's always our first step. Very likely, we won't be able to get quite the performance that we want with just P control. Oftentimes, that's some sort of a transient desire and a steady state desire that we don't have. Like the proportional has some big steady state error. Often it has a big steady state error. I mean, it could be 50%. Like it could be some really bad, huge steady state error. Also the transient, I mean, it might be too slow. Oftentimes it's too slow, or it overshoots too much, or whatever. So we do what we can with it. But then we design a lead controller to improve the transient response. That's our first step. So we'll learn how to do that part. And then we simulate to make sure that the transient response requirements are met. The reason we have to simulate, as came up earlier, is that we have to make sure that the actual system that results, which is likely not a second order system with no zeros in it, so that analytic prediction for what the transient response should be is probably not quite accurate. So we have to do a simulation, or technically we could also solve the differential equation analytically if we wanted to as well, to see if we meet our transient response requirements. The next step is to simulate the system to check the transient response. Oh, I did that. Then we'd redesign and tweak it if needed, so maybe we didn't meet it. So one of the things, I think I designed the first problem, or second problem, it's hard to say, of the exam to be such that if you follow the design steps with a second order approximation, you're not going to meet your spec. If you just follow it straight, you're not going to meet your spec. And so you have to deviate from that to meet your spec. And that is sometimes needed in step 4. Sometimes maybe we don't meet our spec by just following it because the second order approximation doesn't hold. So we think that if we put our poles here, we're going to get this settling time or whatever, but it actually is longer, or the overshoots more or something. And so what do we do then? What is our thing? So redesigning and tweaking is necessary. I would say in general, the way that I tend to approach this is that if you have a spec, like say you were aiming for 10% overshoot, and in the end you ended up with 15% overshoot, it's probably the case that if you design for, instead of aiming for 10, if you aim for like 5, then you might come out and actually meet your spec. So you start to become more conservative with your analytic approximation guesses early on, and then you say, oh, okay, well, I tried it with just, right on the bleeding edge of my spec, and it didn't work out. So now I'll be conservative about it on my second pass and say I was aiming for 10%, so I'm going to actually say I want 5% overshoot, and then see if it comes out to meet the spec. And that is almost always an effective way to approach that if you have that issue arise. It's not always, it doesn't make for like beautiful demonstrations because you don't like see the sort of response that you were hoping for to come out. But then, it's a realistic thing. So you have to then recognize why. Oh, it's not actually a second order system with no zeros, so I'm going to get a different response, and then you have to adjust accordingly. So it usually works out as long as you are just more conservative along the way. So then step 5, so now we've got a system that hopefully meets our transient response requirements, and most likely will still not meet our steady state response requirements. So at that point, you include lag compensation to meet steady state error requirements. So first you have to evaluate the steady state error, see if it meets it. If it doesn't, then you add in lag compensation to meet the steady state error requirements. And then you simulate to see if that actually occurred. So you designed it so that it would, but once again, you're basing your assumption. So you're not only going to evaluate your steady state requirements, make sure that those were met, but you also are going to reevaluate your transient requirements. So hopefully you didn't affect them too much, and you could have when you added in the lag control. You try not to, but it can happen, and then we just redesign and tweak as needed. And some of this might feel a little bit like we're just sort of like loosey-goosey, kind of like waltzing through these problems, and we're just saying, well, let's try this, let's try that. That is actually the recommended way to do it. There's really not really a better way to do it. You sort of wander through trying something, and if it works, great. And if it doesn't work, you have to adapt and try to come up with a little bit better design. So you kind of use these guidelines to go through the problem, but they're not always going to be perfect. So, like I said, it's a guideline. It's always going to be iterative, and this sort of idea that you can go linearly through steps 1 through 8 is sort of a useful fantasy. So let's do this problem from Nice. So given the unity feedback system here, so of unity feedback, find the transfer function of a lag lead compensator that will yield a settling time of 1/2 of a second shorter than that of the uncompensated system, with a damping ratio of 0.5, and improve the steady state error by a factor of 30. So with lag compensation, we're not talking about going from finite steady state error to 0 steady state error. We're talking about reducing it by some factor. Okay, so we want to reduce it by a factor of 30. The compensator 0 is at -5. So this is a piece of information that is given in the problem only so that most students will come up with similar designs. It's actually kind of arbitrary where you set the compensator 0. So they specify it only to make everybody get about the same values. So keep that in mind. Also, find the compensated system's gain, justify any second order approximations, or verify the design through simulation. So that's the problem. So notice this is a 4th order system. Super scary, right? So that's happening. So the first thing that we do, step 1, is evaluate the transient response with P control. So we want to see, how well can we do with just P control. We'll look at a root locus plot, and we have a pole at -2, -4, a pole at -6, and a pole at -8. And so the root locus is on the real axis there, and on the real axis there, and then it splits off this way, and this way, and this way, and this way. So first off, tell me things about the stability of this system. I mean, I don't show the whole root locus, but yeah, it's going to go unstable as you increase the gain, right? This branch is going to head off into the right half plane. It's going to become unstable. So for high gain, you're in trouble. Also for, these two poles here are going to be your two dominant poles, right? This pair that splits off here, because they're going to be much closer to the real or to the imaginary axis than these ones out here. So you have two poles that are probably your dominant poles. They might not be a large factor closer to the axis unless you get to higher gains. But if you're at low gains, second order approximation starts to look a little sketchy, not so second order anymore. You're kind of stuck on this root locus, right? You can't move off that. So our transient response requirements are specifically going to exclude the possibility that we can do proportional control alone, because it says we have to do a half second better in settling time. So if we only had the damping ratio requirement for our transient response, we would be good to go. We would find our damping ratio ray of 0.5, which is something like this ray. And we would say, what does the gain need to be to get on that line? I guess it's more like that. What does my gain need to be to get on that line? I would choose my gain, and then I would say, okay, on to the steady state. I don't even need to do a lead controller because I don't have to get it. Apparently, time is of no object in our design. But it actually is. We want to be a half second faster than whatever we can do with proportional control. So, all right. So we're definitely going to need to do a lead controller. And so we use MATLAB to find the gain required to at least be on that damping. We can at least meet the damping requirement, which is equivalent to having what other requirement? There's another, the what? The percent overshoot. Yeah, so it's the overshoot and the damping ratio are the ones that are essentially 1-to-1 matching.
Well, it's related to settling time too as well, right?
It's also related to settling time, but so damping ratio and percent overshoot are directly related. And there's if you know damping ratio, there are no other parameters that you need to know the percent overshoot based on the second order approximation. The settling time, you also need to know the natural frequency. So you need two parameters for settling time, whereas you only need one for percent overshoot. So, okay, so we've got the damping requirement already met by our proportional control. And I said that in MATLAB that took a gain of 355. Let's go ahead and open MATLAB and let's do that. So I define the system, the uncompensated system here, there are no zeros in this problem, and there are 4 poles. So I just plop those poles in there and do a root locus. So if I stop it here and I evaluate it, I was a little excessive with the number of this again. You guys, last night I was having my machine crash repeatedly. I don't know what was going on. Well, I think it was a disk error. I did disk utility and well, actually that didn't work, but I did this other command line one and I got it to, I think it repaired the disk, the volume. But it did have one more crash after that, but it's been pretty stable since then. It hasn't crashed, but it was just like, it wasn't even going to like spinning wheel of death or anything like that. It was just shutting down, just boom, shut down and then restart. It was really scary. I was like, So I was up at like 2:30 last night trying to like figure out what was going on with this machine.
Don't worry, there's a dongle for that.
There's a what?
There's a dongle for that.
A dongle for that?
Yeah, because the new MacBooks, you can't plug anything into it. You need a dongle for everything.
Oh yeah, there's a dongle for that. Yeah, I have Apple Care, so I have like a warranty for another like 3 months, I think, something. And so I'm hoping that if this thing is going to start going on the fritz, it does so like not right now, but like maybe Sunday at the beginning of spring break. And then I can go. There's not an Apple store in Olympia. I got to go up to Tacoma to go to the Apple store, which sucks. But anyways, at least I'm still on warranty, so if there is a problem, they'll fix it. Okay. So let's evaluate this again. And my screen will be correctly sized this time. Aha. And we have a damping of 0.5, so let's go somewhere in there. We're close already. And I made this ridiculously highly resolved, so I don't know why I got that precise about it, but 355 is a gain that gets us to damping of 0.5, which corresponds to a percent overshoot of 16.3. And the pull is at negative 1.53 plus 2.65 in the imaginary direction. So let's, I didn't write that. Let me get my notes out. So we've got our starting closed loop pull location. Notes are all a mess right now. I wrote myself a note at the top of these notes that 1 is never 0. I made that note just to make sure that we were aware 1 is never 0. These are the exams. I need like a studio to do these lectures anymore. All right, so we have the settling time. Our second order approximation tells us that our settling time is equal to 4 over zeta omega n, right? And zeta omega n, you may recall, is the negative of the real part of this pole location. Remember that geometric interpretation of what zeta omega n is? This is at negative zeta omega n. So the settling time, I often just think of it as being 4 over whatever the real part is. I don't even think of it usually as zeta omega n. I mean, it's good to know that. But so that's equal to 4 over 1.53, so 4 over 1.53, which is equal to 2.61 seconds. Okay. So our requirement is to be a half second less. So our design goal is to be at TS prime equals TS minus 0.5, which is equal to 2.11 seconds. No period, which implies we need to scale the pole by a certain amount. We want to stay on that damping line, right? stay on that damping line, if we think of it as being a vector starting at the origin and ending at that original closed loop root location, closed loop pole location, if we want to move along that damping line and we want to move to the left, but always along the damping line, we just want to scale that vector, right? And to scale, we want to scale the real part by a certain factor, and so we want to scale the whole thing by that factor. So what the scaling factor, I'll call it A. We want that scaling factor to be our new damping ratio and our new natural frequency divided by our old damping ratio and our old natural frequency, which is essentially the real part of the new one divided by the real part of the imaginary one, or sorry, of the old one, equals, if we use that formula to relate, it would be 4 over Ts prime divided by 4 over Ts. And that turns out to be just Ts over Ts prime. So what we want is for our factor that we scale the pole by, it needs to be 1.237. Okay? So if you just plug in 2.61 divided by 2.11, it's approximately 1.237. So that's our scaling factor. Therefore, the desired closed loop pole, so this is sometimes we call it the test point, so I'll do TP in the, so STP in the subscript there. So A is our scaling factor by the original one that we got from just using proportional control, plus J 2.65. So this was the original pole location. And that gives us negative 1.89 plus J 3.28. And in MATLAB, we did just that. So here's our original proportional pole location. The best we could do with our proportional gain, when we got to a gain of 355, we saw that this is the location of the closed loop pole, the dominant closed loop poles. So we have the settling time prime is -4. I mixed up the prime and the unprime on the notes and then in this. So in this one, the P is the one that is the original one, and then the non-P one is the desired one. That's confusing, but in any case, STP of on the real part of the test point is -4 divided by the settling time that we want, and that gives us this relationship here. So I'm essentially doing these same steps to compute that the scale here, I don't call it A, but the scale here is this. So what does our STP end up being? I don't know if I defined it already. STP is 1.89 and then 3.28. Negative 1.89 and then 3.28. So there's our test point as computed using any number of ways you could do it. I just wrote like 3 different ways here, and then I did it a different way here. So in any case, all you need to figure out is it's like a similar triangles. What do you need to scale to get to that other point? So then I defined the closed loop proportional controller just for comparison purposes, because later on I'm going to want to use that in the simulation. Okay, so there was step 1. So we can see that this is off the root locus in this first figure. So we want to be at negative 1.89, 3.28, which is, somewhere in here. We want to be somewhere like there, and we're off the root locus. So we need to use lead control, or we need to use derivative control, or compensation is usually how we say it. So there we go. So step 2, design a lead controller to improve the transient response. Okay. So now that we know the test point STP, we can design the lead compensator. The location of the 0 is arbitrary, but sometimes we choose it to cancel a pole and lower the system order. Once again, all those precautions about canceling an unstable pole still apply. I just wanted to reiterate that. Don't do it unless you are do it, but just be aware of what you're doing. That it can still be an unstable system. So here we choose not to cancel a pole. Instead, we place it at -5. And that was pretty arbitrary. The problem specified -5, so we just went with that. But we could have chosen really anything for that 0. Part of what goes into choosing it is that where you choose that 0 to be affects the how you are going to instantiate the controller. So you might end up having to adjust where you choose that 0 to be based on selecting capacitors and resistors and stuff. But it has no effect mathematically. So it's arbitrary where you place it. So you can place it anywhere. So we want the relocus to go through STP. So we have to figure out the pole's angle contribution required to make that happen. Okay. So that is what we're computing in this next formula here, based on the angle criterion. And I highly recommend using MATLAB for this part, because doing this out by hand is a big mess. But essentially what you have to do is you have to evaluate the transfer function, which is your lead compensator multiplied by your proportional controller together. Evaluate that angle at your test point, and then add pi is how the trigonometry works out.
So is that angle just the angle of that one point, or is it all the sum of all the angles?
So if you remember, if you evaluate a transfer function at a given point in the complex plane, what it gives you is, so we were at one point able to interpret that as being as always matching the magnitude criterion and always matching the phase criterion. So the magnitude and phase criterion are related to each pole and 0 from the transfer function. And that's why we are thinking about like all the poles and all the zeros contributing to it. So when we evaluate this transfer function at any given point, all of the poles and zeros are contributing to how that function evaluates at that point. So that's kind of that's like, it's hard to explain without pictures, but
No, I mean, I've done it by hand to try to match the hand calculation to that, and I was having a hard time doing it. But
yeah, I haven't done a thorough set of notes on that, but I should do that. Maybe I'll be able to find some time in the next couple days to do that, because it would be nice to show you that that's the case. So the angle,
I mean, so would it be all like minusing all the poles, theta poles, and plussing all those theta zeros, and then you add 180 to that, and that should be the angle?
yeah. So the angle criterion, remember, is this. So if I can remember off the top of my head, hopefully I can. Use a light color. The angle criterion said, well, so it all comes from. All right. Let's see if I can remember this. It comes from the fact that the closed loop transfer function is g over 1 plus kgh. Okay? And say that it's unity feedback, so h is 1. So g over 1 plus kg. Okay? Our poles are going to occur, our closed loop poles are going to occur, so when you're on the root locus, they're going to occur at 1 plus kg equals 0, right? That's where the poles are going to happen. And so what we can say from this is that k has to be equal to negative 1 over g. And, right. And if you want to know what oh wait, no. I mean, this is true if you want to find k, but I think that what I want to do instead is say I think we say kg has to be equal to minus 1. So we want to know when kg equals minus 1. That's the sort of the basis of our angle and phase criterion. The magnitude criterion comes from the fact that kg, the magnitude of it has to be equal to 1, because on this side of the equation, if you took the magnitude of both sides, you'd say the magnitude of kg has to equal 1, right? So magnitude of negative 1 is 1. The phase of kg has to equal, what is the phase of negative 1? In the complex plane, it's 180 degrees, right? It's pi. So there's negative 1. So the phase is pi. So the phase has to equal pi. Go back to my white. Has to equal pi. And if the phase is going to equal pi, the interpretation is that anytime you evaluate a transfer function, at any point, you can think of the magnitude as being the product of all of the distances from each pole to that point. So if we have, in the complex plane, let's take a system that has a, say it has a complex conjugate pole pair. Can you guys see that? Nope. Has to be pretty much white then, huh? So if you've got a complex conjugate pole pair, and you've got like a 0 here or something, if you want to evaluate the transfer function that has this pole 0 plot, then if you evaluate at any point, so say a point like this, just pick a random point, then the magnitude criterion says that if it's going to be on the root locus, then if you took those lengths and multiply them all together, that would have to equal 1. That's what the magnitude criterion says. The phase criterion says that these angles, so these angles from this side, so all the way around on this one, those angles must add up to 180, must add up to pi. And so the formula that I'm using right here is derived from this angle criterion, which is saying that, oh, if I am changing the phase, or if I'm going to make the root locus go through a certain point that I want it to be at, how do I have to construct my poles and zeros such that that becomes true? If you come back and look at this, well, you see that this becomes a sum of phases. So I'll call them like theta 1, theta 2, and theta 3. So theta 1. So I can't remember. I think the poles. I can't remember if the poles are positive or the poles are.
Negative.
Well, the poles are negative when you evaluate it, but I think that in this transfer function, because it has to be equal to pi, I can't remember. I think that it ends up being the opposite. I can't remember if it's negative or positive. We're getting a little bit beyond my ability to just conjure it up out of memory. But theta 1 minus theta 2 plus theta 3, or it's plus theta 1 plus theta 2 minus theta 3. In any case, you're summing these angles together. And if you're going to just place a new pole, the orange shows up, right? So if I'm going to just place a new compensator 0, just like slap it in there, and a new pole, these two are going to affect it. They're going to have their own angle contributions. What you want, so the trigonometry problem that you're doing is you want those angles, so you picked your test point where you want the thing to go through, and you get to choose where the 0 and the pole are to make that happen. But you actually have two parameters to adjust. You can adjust where the 0 is and where the pole is separately. But you only have an algebraic equation that specifies one of those, which is this algebraic equation right here. So you have to arbitrarily specify where one of them is going to be. That's why we set that 0 to -5, and then we can move the pole to be wherever it needs to be to make the root locus go through your test point. Okay? It's there are a lot of details in like going through the trig, but it's not an infinite number of details. Like for instance, we should be able to get whether these poles are additive or subtractive in this, but I just can't remember. I think that if you evaluate them, the poles are negative contributions and the zeros are positive contributions. But in my back of my mind, there's something about that getting flip-flopped when you're thinking in terms of the. And I think it comes into play when you're trying to make the angle pi instead of making the angle. Yeah. I have to go back and think about it, but.
Yeah, so the book has something like that, and then it's equal to what, 2k plus 180 or whatever it is.
2k plus 1 times 180?
Yeah. And then there's a YouTube video with that Brian Douglas controls guy, and he has it where he's got the theta angles, and then it's theta p minus theta z. So, and that's kind of the two that you're trying to figure out.
Yeah. So if you've got these, if you called this, if you called the angle for this guy theta p, you called the angle for this guy theta z, the 0, then you're also going to have minus theta p plus theta z. And this all has to equal pi. Or 2 pi times, or 2 pi added to it, or 4 pi added to it, or whatever. So you have to solve essentially for the difference between theta p and theta z. That's what you're solving for. And you can then specify arbitrarily where one of them is, and then that sets the whole thing. So that's what we're doing here. There's nothing magic about it. It's just working out the trigonometry. And the way I did it is I just did it once, and then I just put it into MATLAB, so I didn't have to derive it every time. But yeah, it's essentially just matching up that angle condition.
You got it right. It's on page 470.
On page 470, is like this?
Yeah.
Sweet.
But it's 2k plus 1 multiple pi. 2k plus 1 times pi.
Yeah. So 2k plus 1 times pi. So what that means is it's pi plus 2 pi times the gain. So
Any odd multiple of pi.
where k is different. K is not the gain. K is I'll use n. Where n is an integer. So cool. Yeah, and I mean, I might as well just solve for it when it's pi. I mean, leaving that, it's generally, this is true, but might as well just solve for what makes it pi. Because yesterday was Pi Day, if for no other good reason. What the hell is Pi Day? I see internet things about it. Like, seems like half of the time it's like an engineer, engineering thinks it owns Pi Day, and math people pretty much like it's like Nerd Day, or it's like about eating pie. Like, I think it just doesn't understand. Like, I think that it's just there's a bunch of people are claiming Pi Day.
Happy National Arbitrary Day.
Yeah. I don't know. Okay. Anyways, if you go through that calculation, or you do that calculation one time and you put it into MATLAB, so you don't have to always do that calculation, you get the angle contribution for the compensator needs to be 14.37 degrees. This is for the pole contribution. So I drew it here. We have this test point that we want the root locus to go through. And z lead, we said, is at -5. So we have to choose theta c such that, so place the pole such that theta c contributes the right angle. And the right angle is going to be 14.37 degrees. Essentially just going through that argument. So this implies that you need, so if you calculate that angle to be 14.37 degrees, you still have to calculate where the pole should be. And that's a simple trigonometric argument there. The real part of STP is this distance, right? Is that distance. And the rest of the distance out to your pole is just this side of a right triangle. So, trigonometry again. Or you could use geometry. Also would work. Yeah.
Right, when you're finding that angle, why did you multiply by SCP plus 5, or what does that mean?
This is because we have we already put the 0 in the compensator. So we stuck the 0 in the compensator, And that already made the root locus go to whack. Actually, we didn't plot the root locus for what happens there, but we're assuming that we've already got the 0 in there, and we need to find out what contribution the pole needs to make.
So that actually wouldn't be STP, it would just be S, right?
Well, it's S, but we want to evaluate it STP because we want to know at that point how much. Because remember, we want to make sure that we go through that test point. So all of the stuff out here was just at any value of S we would evaluate it at, just for some arbitrary S. But we specifically want to go through STP. So if we evaluated STP, then we have to make sure that this holds at STP. Not just anywhere, because, I mean, obviously it can't hold everywhere, because the root locus is just going to be a line and a plane, so it can't hold everywhere. It has to only hold in certain places. So your STP is where you evaluate your transfer function, your compensator transfer
So
function.
that's not like saying S plus 5, it's like, no, it's like saying that's a 0, right? Times the transfer function to make a new root locus.
So this,
Actually, a point is a complex number.
yeah, this is a complex number, which is why you can take an angle of it. So this is like the compensator. The compensator when you just added the 0, well, you just put the 0 in, but you haven't put the pole in yet.
Right,
That's
so
what
that
all
would just be a real number, -5.
Well, STP is complex. STP is this point.
Yeah.
So STP is we calculated it to be -1.89 plus J 3.28. So that's a complex number multiplied by another complex number. So you get out a complex number. This is just a new transfer function. I mean, we could have called this something. We could have called this H or something. Or G2. Or G6. Couple of you are giggling at that.
Well, no.
So you could call that, because what this is our forward path. Ooh, that's getting light. Our forward path transfer function. So we've got our forward path transfer function, G. And then we've got our compensator that we're building here, right? We're just building it piece by piece, though. And we've got in here, we're going to put a pole and a 0 for our lead compensator. So we've got an S plus, or S minus our 0, you could say, ZC, and S minus our pole location. So that's what we're going for. But what we're saying is we want to know the angle contribution if we use just this part and we just combine it in there. And we need to know what angle contribution this guy needs to make in order for us to go through our test point.
I completely agree, but your
Yeah.
notation should be just Laplace S and not STP, right?
Well, we're evaluating it at the test point.
So that's just a notation thing then. That's not the 0 times the transfer function at that angle. It's right.
This is the transfer function of the 0 contribution. So this is so STP is not equal to ZC. If that's what the hang up.
That's what my hang.
Yeah, so STP is the point we want the root locus to go through.
Yeah.
That's what STP is. So in other words, you're not just multiplying this by 0. You're not multiplying. This is not -5.
This is not just the compensator times the plane, right?
No, So this is, so we've got G. So what this is S minus ZC times G of S. So we've now combined the numerator of this and G together into one transfer function. Now, ZC is -5, right? So ZC is -5. We want to evaluate this at STP, which is the location we want our transfer function to go through. And it's not just the 0. What we want is for it to go through STP, which is this point here. We want our root locus to go through it, which, I mean, it's showing it going through it because I've already done this in the root locus that I've specified, but this is the test point that we weren't able to go through before. Remember, up here, this was STP as well. We want to go through there. So that's why we evaluated that point, and that's why it's not. So if it was 5, you're right, it would just be multiplying it by 0, and it would be wiping it out. So you're not multiplying it by 0. You're multiplying it by is whatever STP minus 5 is, which is some complex number. It's so STP minus 5 would be -6.89 plus J3.28, right? So that's what that would come out to be.
In MATLAB code you have written,
Yeah, it's not how you do it in MATLAB code.
you have the STP equaling what in your notes would have been the prime portion of -4/TS divided by, then you have the real SP times SP.
Yeah.
A complex times the real portion, so you would have had the real portion squared.
So it's like a new transfer function evaluated at STP.
Yeah.
What I read that as.
So, okay, what this is so this is a new transfer function that is equivalent to S minus ZC, okay? I need to get like a light color on my auto ones. So that is this portion, that ZPK thing, okay? And then sysp is just G, okay? Now, so we got those. And now I'm going to evaluate that at S equals STP. Okay?
Yeah.
Let's do it. So S equaling STP is
Operating at a higher level.
-1.89 plus J times our ZC was 5, right? Our STP was 3.28 plus 3.28. So it's that. And then, so that was our S equaling STP minus ZC. So minus ZC, which is 5, right? And, oh, wait. ZC is minus 5, right? Plus. Times G, which is all of this stuff. So I'm not even going to write it. Well, I'm going to write plus G of STP. So plug in STP everywhere. Or G of, I'll plug in what STP is, -1.89 plus J 3.28. So this first term turns into so 3.89. No. 1 plus J 3.28 G of minus 1.89 plus J 3.28. Right?
Yeah, all right.
Okay. So we tracking now?
Yeah, totally.
Okay. Sometimes you just got to go through it. Sometimes you just do it. Okay. I kind of like the dark theme. Dark theme's kind of cool. It doesn't show up very well on a lot of screens though. So. It is. I heard somebody go through an argument once about whether or not Google could like appreciably change the global power consumption by changing its homepage from white to dark. And the argument, I don't remember how they came up with the conclusion, but somehow they came up with the conclusion that it wouldn't affect things, really. And I don't know, it had something to do with the way the screens are like already have to be on, consuming just as much power, even if they're projecting darker colors. I don't know.
Mostly the backlights don't change much for most screens. They just have, the backlights are just like a white LED and they're always on.
Okay.
That's most of the power consumption.
Okay. So yeah, so apparently it isn't actually going to save a lot of power, but it was cool to think about anyways. So, all right. Well, I'm glad we had that discussion. Sometimes we just need to go through it. And I probably glossed on it when I went through it the first time. So we probably got more detail there than we had before. So that was good. Good. So now we just, we computed where our lead pole needed to be. So we chose our 0. We found where our pole needed to be through a somewhat painful process. We made it. We found our pole location. So from the root locus of figure 2, the required gain to achieve this test point now, which now our root locus goes through the test point. Thank goodness, after all of that, it does. We need to compute what the gain should be. So back over here, we do that. And if we look for our good old damping of 0.5 points, we get 1.36 times 10 to the 3 for our gain. One of the reasons why, so you can get more precise with this stuff, like reading it off the graph, even if it's just giving you a little digital thing. It only has like 3 decimal places or whatever. It's not super precise. One of the reasons why I don't sweat it is that this is all approximate anyways, right? So that's why we just sort of like, I'm usually much more careful with things, but when you're doing approximations anyways, not that much of a point in being super precise about an approximation. So I don't worry about it. So we do that, and we chose 1.36 times 10 to the 3. And we made that controller for simulation requirements. So let's do the simulation to check the transient response. So we did this lead control design hoping to improve the transient response. And so let's do that check. So here was the response with the P controller, which we hadn't actually simulated explicitly yet, so we did it this time. And here it is with the lead compensator included. Eyeballing it, it looks like we improved by, a decent factor in the settling time, but it's a little hard to tell by eyeballing it if you're precisely there. So let's do a little bit more analysis of it. So visually it looks good, but we should check closer. So if you use step info, you can do the proportional step and the lag step. So I put them both in there and the time vectors, and I check for settling time improvement. So you can actually select out settling time by using this dot notation. So p step dot settling time gives you the settling time for that response. Lag step dot settling time gives you the settling time for that response. And then you can print out what the improvement is. So let's do that. Improved by over half a second. And so that's good, right? We wanted to improve it by a half a second. We improved it by over half a second. It's probably, it's good that we're a little bit on the safe side because you never know what's going to happen when we do our lag control. So let's evaluate. So our next step, our step number 5, is to evaluate the steady state error for the lead control system. Now, just looking at this, ain't looking so hot, right? We're off. This should be at 1 in steady state. It is at 0.54, something like that. So it's got almost 50% error, 40-something% error for steady state. It's bad news. You don't want that. So from the figure, we see that we need to have some improvement in settling time. We had a little bit of accidental improvement with the lead compensator, but that was accident. Yeah.
I printed black and white. Could you tell me which one is which on that?
Yeah. The one that happens a little bit faster and that goes higher is the one with lead. So that one could be dashed. And then dashed there. Wow, there's like some colors that just don't come through at all on this.
It seems like the world's worst projector.
Yeah, it is. It's pretty bad. Whoa, look at my skin shows up really funky on there. Jeez. Whoa, I just look like 2 eyeballs coming out of like a skeleton face.
That's probably more the webcam. Webcam tries to balance colors. You get different backgrounds when you change your skin color.
I look better down here. I'm telling you, I look better down here. Up there, I look really weird. Okay, so from MATLAB then we found that our actual so up here I was using it a certain way and I switched. So TS minus TS prime. So I didn't switch in my notes. I just switched in the MATLAB script. Is equal to 0.555 deal? I don't know. Is this Domino's? 555. Wasn't it Domino's? Herman Cain! He was going to give us the tax 555 deal. Remember this? Back when politics didn't suck so much? Back when it was like, oh my God, maybe Herman Cain and Domino. Wasn't he like Domino's or Papa Murphy's or something CEO? Just something like that. And then like stuff hit the fan when like a bunch of people started coming out and saying he's a rapist. I don't ever know what happened with him. It did. It was all fun and games. It was all 555 deals, and then it was like, oh, but he molests women. Oh. That probably has something to do with Jared. Okay. Evaluate the steady state error for the P-controlled system. So, we know it's not looking good. But we want to evaluate, we want to be precise because we want a 30-fold improvement, so we got to know what it is now. So assuming that we're designing for a step response steady state error, which is typically the case. If we don't specify, then it's step response steady state error that we care about. We can find the static error constants of the P-controlled system. So remember when we would compute the static error constants of these things back in the good old days? We took the limit as s goes to 0 for a step response. This is the error constant. It is the proportional gain. Don't forget the gain term, otherwise you end up with an answer that's way off. So if we do this, look at our g of s, what happens if you plug in s equals 0 in there? It's just the denominator becomes 2 times 4 times 6 times 8. And don't forget to put your gain in. And we come out with 0.9245. That's our static error constant, which gives us a steady state error. You can plug it into the formula. Steady state of the proportional system is 1 over 1 plus k pp.
And that KP that you're using, is that the 1300 one?
Yeah.
Okay.
Yeah, that's right. Well, KP would have been the first gain that we computed. So that would have been 355, right? I didn't write it here. It was just over in MATLAB that we did it. So that would have been 355. So the steady state error is 1 over 1 of that, which is 0.5196, which is pretty much what we saw. So that makes sense. But our requirement is a 30-fold decrease in this. So working backwards, we have that the steady state of the lag lead should be equal to the steady state error of the proportional system divided by 30, right? We want a 30-fold decrease. So we say, okay, if we plug this in there, we need this steady state error to be 0.0174. And let's compute what the static error constant should be then. What is KP for the lag lead system? It's essentially this same formula, but solved for KPP, but KPLL in this case. So that's equal to 1 over E steady state lag lead. Getting a lot of subscripts here. Minus 1. And if you compute that, that's 56.32. So that's what we want for a static gain constant. We know that in order to get this, the lag controller must have a 0 over pole ratio of 61.37, which is found by just dividing what our desired KPLL is divided by the KPP that we computed. So if you divide this by that, allegedly you get 61.37, although it doesn't look right to me. Something's wrong there, right? Because if I look at that, that should be like double, essentially, if you divide it by 1/2.
You're looking at ESSP.
Oh, that was what. Yeah, that was it. Good call. KPP. Aha. That makes sense.
I got 60.92.
Okay. So we're good. We're right in the ballpark there. We're just working with round numbers. All right. So that is the 0 over pole ratio we need. So in the case of the lag, we stick the pole close to the real axis. How close? Kind of depends on how fast you want the system to respond, how much you're willing to sacrifice transient for steady state. Usually we start off pretty conservatively. And then we might try to increase the speed and see how it goes. Yeah.
Isn't that minus 1 after the fraction, not on the bottom?
Let's see. So solving for k. So over there.
Having it on the bottom would give you a negative number.
You're not wrong. So let's see. E1 plus k equals 1. So k equals
Yeah, the math works out if it's outside of
equals 1 over e minus 1. Is that right? Yeah. Yeah. So you're right. This belongs. So correction. The minus 1's out here. Huh. What do you know? An issue in my notes. Typo, or righto, or whatever it is. Okay. Yeah. Good call. So now include lag compensation to meet the steady state error requirement. So let's arbitrarily, somewhat arbitrarily, place the lag pole at negative 0.01. Very conservatively here, we're going to try to not affect the steady state, or we're going to improve the steady state error, we know, but we're going to try to affect the transient as little as possible. But it affects the transient in another way. The steady state part of the response, the sort of the lag part or the integrator part, comes on slower if we put this closer and closer to the real axis. So we're doing that. We're going to come up with a design that actually, in my opinion, we should be a little bit less conservative on, and we'll do that. So so the zero lag must be, you got to use this 0 over pole ratio to figure out where the pole should be. Stick that out at 61.37 times p lag, so at negative 0.6137. And so this shows that our lag pole is there, our lag 0 is there, and the controller then, if you put it all together, is GC of S equals KLL times S plus 0.6137 times S plus 5 divided by S plus 0.01. Oh, wait. We also have a pole here too, right? Another pole that came from up here at negative 14.68, right? So S plus 14.68.
Can you narrate that numerator? I can't read it.
Yeah. So the oops. I have a typo in my note for typo. Isn't that funny? So the numerator of this has the 0 from the lag controller that we just designed, right? Which, so this pole, or sorry, this 0 is showing up right here. And then this 0 comes from our lead design where we just arbitrarily plopped our 0 at 5. This pole is coming from our lag that we just did. And this 0 is coming from the lead pole that we computed. So this one is that guy. This one is that guy. This one is that guy. And this one is that guy. Yep. That's clear, right? Okay. So let's do that in MATLAB then. So I just did all the calculations there. Oh, and look at that. There's my -1 properly in there and not strangely in the denominator, like where it doesn't belong. It's like I read it off and then I wrote it and I didn't pay attention very well. So then we stick that in and we look at our new and improved root locus that goes through our test point but has just enough steady state error improvement, hopefully, for us. So 1.35 times 10 to the 3 gets us to our test point, so that's our gain. So simulate the system to check all response requirements, and this is what comes out. Let's take a look at that. Boom. So questions that we have. Did our steady state error improve that much? Is our transient response still okay? Transient didn't change that much when we added the lag, but it did get a little slower, so we should probably reevaluate that. We have a really slow, I don't really like how slow the lag is helping out here. That's a slow response. If you care about a settling time on that, you want to make it a half second faster, and it was already just a couple seconds, you probably don't want your steady state to improve slowly over the course of a while. I mean, it does, even the initial response is quite a bit better, but it's still not as good as we'd want it to be. So, in my opinion, we should go back and tweak. So let's do that tweaking thing. Let's do it for fun. So what happens if I choose my pole? So mostly how we're going to try to approach this is we choose this lag pole to be a little less close to that axis. So let's make it -0.1 instead of -0.01. Okay. And let's see. We have to choose our gain again. So let's go to around 0.5.
What did you change?
I changed our lag pole location. I changed it from we chose it to be at -0.01 originally, but we're gonna make it -0.1 instead. Because the reason it's so slow is that we have a closed loop pole so close to that real axis, and that makes things slow. So that's why we're sticking this in there. We say, oh, okay, we'll make it faster by moving that a little to the left. That's going to speed it up. And it means that we have to change what our gain is significantly. So our gain needs to be somewhere around like 197 or something like that, right?
Is there a way to change the resolution of how quickly you click through those
Yeah.
lines there? Like when you're using your arrow pointer?
Yes. Well, it not directly. So the way that it does it is it just chooses different values of S to evaluate it at, or omega to evaluate it at. If you specify though a range, a range of gains is how you specify it. You specify a range of gains explicitly in the rlocus command, and then it'll plot those. So I actually do that here. I did it in steps of 1. You could do it in steps of 0.1, and it would have a lot more points. It just takes longer to plot.
Because like one of my homework assignments, I was like, it says find a specific game, and I couldn't get it there. I was like, you know what? I'll just do it by hand. And
Yeah.
doing it by hand, I was like, this is
I
awesome.
show it in the some of the examples that I put up there.
I remember talking about it now that you mentioned it.
Yeah, so just check that out. But yeah, so this gain changes from 1300 to like 200, right? So 197. So that's significantly different. And so now let's see. We definitely changed it quite a bit. Let's see what it looks like now. So
It's like steady state error.
it's looking like our steady state error is not as improved as it was before. And I think we're running into second order approximation issues here. So our steady state error is definitely not 30-fold improved anymore. So let's look at the root locus again. I think what we're running into is that this pole is getting too close. So, yeah, so we can't, I would say maybe let's try, I don't know, let's try something in between there just to see if we can get a little bit better. Like 0.05. And let's choose our gain, expect it to be somewhere in between those values. $5.46. Okay, and then let's see what it looks like. It's looking better. So we're kind of trading off like some steady state error and some. But look at our transient is really screwed up too though. It's super slow. So really we as much as we would like to, we're kind of getting screwed up with that. So we really do need to have it pretty close to the axis to keep away from everything else. So let's go back to 0.01 and then
By improving our steady state, though, didn't that directly get rid of what improvements we did to our settling time originally?
I don't think. Well, so if you look, I think it's not bad. We can be a little bit more precise about it. But if I zoom in on this region here, it's closer. It's closer to the original lead one than the P controller one is. It's been closer to that. So I would say we did lose a little, but I don't think we lost a lot.
Isn't that supposed to be from where it falls within 2% of the steady state? So you don't fall the steady state till way towards the end. So
Yeah.
Wouldn't your settling time technically be the entire distance all the way until you got out within 2% of your settling of your?
If you interpret it strictly, that's true. Yes. So your steady state error. Well.
So how do you know when to interpret it strictly and when not to?
Yeah. It's a little tough. It's a little tough. It's essentially what it comes down to is if you didn't have that steady state error improvement, this thing would have settled out to be about 0.81 or something, right? And in that sense, it settles down to about that pretty quickly, and then it slowly oozes up to the steady state value. So it's not very precisely defined. I've never seen anybody actually try to precisely define that transient response, but
So how in the end can you justify that what we've done, all the way down to the end, would be the top curve?
Yeah.
Right?
it's definitely the best option we've got so far.
Can we just keep adding zeros or something to try and increase that settling?
Potentially, yeah. If you want to work within the framework of just lag leads, you couldn't do that. But if you wanted to just go outside of that, you could add zeros if you wanted to. We could also go back and something that I would try to do, probably the next step I would do, is say, let's go back to the lead design and let's try to make it faster from the beginning, because what happened, one of the problems when we were doing the lag at the end is that we started to degrade in our performance, our transient performance, as we got less steady state error or a faster steady state response. And our initial design, if we're more conservative with that, by making it faster than we even want, like instead of decreasing it by a half second settling time, maybe we decrease it by like a whole second or maybe even more in settling time. And then we do the lag design and see if we can't do better in that case. So that's why it's really iterative, and it's really not, there's no linear path through this.
Well, this sucked. Let's just try this. Alright, cool. That works. Done.
Yeah, I mean, it is kind of like that. I mean, it's kind of, I mean, you don't go through blindly. You go through with an idea that, okay, if I choose this way, it should get a little bit better, or it should get a little worse. So you could add another lag controller as well, right? You could add another lag controller. There's no reason that you can't, and that might help you, it might hurt you. It's really hard to say given any situation. So always think, though, that you're shaping this. You're shaping this compensated root locus, okay? And keep in mind that your second order approximations, the more poles and zeros you have, the less effective your second order approximations are, less accurate they are, and the less effective those design tools are based on it. So, but you can wander around in this, and sometimes you just get totally lost, and it just like gets worse and worse, and you just gotta like back yourself up. Just back yourself up and say, okay, well, that's not helping me. How do I make this better? So start back at the beginning and see if you can go another path. I mean, there are algorithms out there for tuning these things automatically. It's sort of like a world that has a lot of possibilities, though. I mean, you can play with it and auto-tune stuff, yeah. Make your own tuner. Actually, that discussion leads to a discussion that we haven't had yet, and that is on optimal control. So, really, at the end of the day, if you have infinite resources, you can make the system do anything you want. You can just make your compensator something really crazy, and you can place your poles, closed loop poles, anywhere you want them to be. And we're going to talk about that. You can place them anywhere you want them to be. But there's always a trade-off somewhere. So optimal control theory gets into that. And instead of saying, okay, I want my poles to be here, poles to be there, what you're saying is, I have this much control effort that I'm willing to give. I want maybe like the you think of it as being like the average value to be somewhere around this of the control effort, and I want the and there's a certain amount of noise that's in the system, and there's a certain amount of observability in the system, and based on those, you can optimize your design, your controller design. And that's what led down that whole path. People said, well, surely there's some optimal way of doing this. And sure enough, there is. But it has its own quirks as well. So it's not like if you wanted an optimal controller, it isn't necessarily the case that optimal control theory is going to get you a design that is more optimal in the sense that you mean optimal. They mean optimal in a very mathematical sense. It's optimal given certain criteria that you can write down. Your design intuition might not be able to be explicitly stated in parameters, or one of those cost functions, they call them. So anyhow, I'm going to finish off this lecture then, if there are no other questions on it, and then we can switch gears.